Hey there. Hey, Courtney. All right. Hi, ladies. And I think we've got a gentleman or two in the class. Juan, I think there might be a David in the class too. Usually this 130 is made up of a lot of women. That's why one reason I really like teaching this class is a lot of like ladies power. And you guys always do so well. Like the ladies do so well in chemistry. I wish there were more ladies in chemistry. I really do. The men do well too. Don't worry. You guys do well also, but it's just always nice to have a lot of women in a science course. So, ooh, Abigail, are you outside? That looks so nice. Yeah. Yeah. Okay, so we're going to keep working with atom and elements. Just ask you here, any reason why there is a no submission button for the lab due this week? Oh, I don't know. Haley, I don't know. Haley, bother me after class and we can take a look at it or something, okay? Abigail, I'm doing absentee voting, so I don't get a sticker. Just take a picture of your absentee and you can like scratch out the personal information right before you're gonna mail it. Maybe even show me the envelope with the stamp on it so that I know you're really gonna mail it. Yeah, voter registration day was yesterday, or National Voter Registration Day. You can still register to vote any other day. So get that done. I do believe North Carolina is one of the few states during early voting that you can register and vote on the same day for early voting, not for election day. And early voting starts October 15th, right around the corner. So get it done. You have October 9th to register for this year for election. Awesome. Thank you. Thank you. Thank you. And if you're not sure if you're registered to vote, you have the same problem, Taylor. Okay. Yeah, I think I remember you us talking about that, Taylor. I'll see what's going on with that. There's a lab this week. I don't know. Why don't we let's share screen and we'll look at the syllabus and see what's going on, because I don't have the whole thing memorized. I was actually, right before I logged in, I was looking at the syllabus to get an idea of what our week is like this week, next week. So this week, I think the submit button was giving people trouble from lab 6, was it? Is I think the one that's giving people trouble. Okay, so I'll take a look at it and adjust that. Let me make a note for myself. Look at submission. Okay, not sure why. Let's see. Just says there's no submission needed this week. I'll take a look. Because atom and elements are due, it looks like we have it due on the 27th. So that would be this. I have to look at my schedule. I don't even know. That would be this Sunday. Let me look at it and see what's going on with it. What do we have marked on Moodle? Moodle, I have it for the 27th as well. Yeah, so I would like you guys to get that done on the 27th. Let's take a peek in here. Time remaining, 4 days. View all submissions. So no submissions. Okay, I have to go into the belly of Moodle, so I will mess around with that later on today. If for some reason it doesn't work, you can always just email it to me. Like you just send it to me as a JPEG or a PDF, preferably a PDF. So as far as the syllabus, as we're looking at that. So this week, the lecture this week and next week, we're doing atom and elements. We probably won't need all of next week for atom and elements. So I'll definitely want to start getting into chapter 6, which is naming stuff, because we want a good amount of time for practice there. Your next test is not for a little bit. That's mainly because, so it's not until like the end of October. This chapter here and this chapter here are Hardy chapters. So I'm trying to see what's going on with the chat. I don't want to pull up. Who knows? Who knows? There we go. Are we going to go over the test? So we're not going to go over the test. You should be able to access the questions you got right and the questions that you got wrong. All right. I'm not going to go over it as a class, but I will totally go over it after you've looked at your exam and you've gone through the ones that you've gotten incorrect. I want you to fish through and say, okay, this is one I didn't get right, and I have no idea why I didn't get it right. So you got to do a little bit more work on your end, but then I will totally give you as much time as you need to go over it one-on-one, okay? So yeah, the reason that I'm not going over it as a class is because the way that it's submitted in Moodle, everybody gets different questions in different orders shuffled around with different answers, and to try and go over it would be absolutely maddening because I'd have to tell all 38 of you or whatever, we're on this problem, find it in your packet of questions. So go through it on your own and then bug me about it and we'll talk about it. Okay, let's see. No, this is not, you don't want to be doing this. You don't want to be doing that. Stay away from that. All right, there's our atom and elements. So we see how good I am at remembering where we left off. We did metals, non-metals. We talked about the atom. We talked about J.J. Thomson, Rutherford, the structure of the atom, nucleus stuff, yes. Atomic number and atomic mass. We talked about atomic number equaling the number of protons, correct? I feel like we went through that. Yeah, that seems, we did, yeah. Protons equals electrons. We did this, yeah. Okay. Someone giving me some help here. Oh, why? I'll show that up. We need isotopes. You need isotopes. Okay. We do need isotopes. They're really awesome. That's what I did my degree in, stable isotopes specifically. So I am a fan of isotopes. Okay, so isotopes. So we're going to work on determining the number of protons, electrons, and neutrons in one or more of possible isotopes of an element. And then we're going to use different isotopes and their percentages to calculate the overall abundance of the atomic mass. So if you look at your periodic chart, those atomic masses are decimal numbers. So like, for instance, magnesium, number 12, is got an atomic mass of 24.3. So it's like, well, isn't the mass supposed to be the number of protons and the number of electrons? Shouldn't that be a whole number? Well, the reason that that isn't a whole number is because it's averaging a couple different types of magnesium. It's averaging a magnesium, some of them having 24 as their mass, some of them maybe having 25 or 26 as their mass. So what's happening there is the number of neutrons are changing. So when looking at an isotopes, isotopes are the same element, which means they have the same number of protons, but they have a different mass number. So the only way we can change the mass without changing what it is to either take away or add neutrons. So neutrons are going to give us isotopes. Electrons will give us ions or charged particles. So looking at this symbol here, this is magnesium 24. So you're dealing with specifically magnesium with a mass of 24. Its atomic number is always 12 because magnesium has 12 protons. These two things are synonymous with each other. So if our mass number is 24 and our atomic number is 12, then the number of neutrons should just be the difference in those two numbers, right? 24 minus 12 gives us a remaining of 12. So 12 neutrons and 12 protons. So looking at atomic symbols and then how it refers to their subatomic particles, or just how many protons, neutrons, electrons it has. So if I look at this here, this is oxygen. And I would call this actually oxygen 16. It's the specific oxygen that has a mass of 16. So the number in the lower left-hand corner is representing protons, or the atomic number. So we have 8 protons. In this case, to solve my neutrons, I'm going to take this number on top and subtract it from this number, or the atomic mass minus the atomic number. So I get 8 neutrons. And then because this thing doesn't have a charge in the upper right-hand corner, we're going to say it also has 8 electrons. Sometimes that happens where it's 8, 8, 8. A lot of times it's with the smaller elements. As the elements get bigger, the number of neutrons starts to stray from the number of protons. So we can see it here actually with phosphorus. So phosphorus has 15 protons. Its atomic mass, specifically we're dealing with phosphorus 31. This one has 16 neutrons. So the neutrons are starting to get a little bit more. How many electrons? Well, there's no charge to it, so the number of electrons should be the same as the number of protons. We go something even bigger, zinc, we can see that zinc has 30 protons because its atomic number is 30. Those two go hand in hand. This is zinc 65. So we'd take 65 minus 30 to get the remaining number of neutrons, or 35 neutrons. Now the number of neutrons starting to get a little bit bigger than the number of protons. Electrons, again, is going to be the same as protons as long as it's not charged. So in a strip of magnesium, there are 3 isotopes. We have magnesium 24, magnesium 25, and magnesium 26. Now, how many protons are for every single one of these isotopes? 12. Every single one of those, so I'm going to put it as magnesium 24, magnesium 25, and magnesium 26. 26. This is just a different way of writing these 3, okay? So for magnesium 24, number of protons, always going to be 12. That's the definition of magnesium, is that it has 12 protons. My neutrons, in this case, are going to be 12, right? 24 minus the 12 gives me 12. For magnesium 25, protons, still 12. Doesn't change. Neutrons have shifted, though. This is a little bit heavier. So 25 minus 12 means I'm going to actually have 13 neutrons. Magnesium 26, protons, still 12. Neutrons, on the other hand, for this one, a little bit heavier than even the one before it, it's going to be 14 neutrons. So as we increase the atomic mass of our isotope, we increase the number of neutrons. We don't change protons. I didn't ask you specifically how many electrons there were, but because none of these are charged, electrons will be 12 for each one. So any questions on how to read these? Sometimes you'll see the mass for that specific isotope written in the upper left-hand corner. Sometimes you'll see it written behind it, like magnesium dash 24. There's a few different ways we can see it. So here's that same thing that we talked about. One way to write it, all the protons, 12. All the electrons, 12. Mass number is shifting, so number of neutrons is shifting. Sometimes we'll give you the actual mass of the isotope, which is, it's going to be really, really close to this number, but it'll be a slightly decimal version, so 23.99. If they ever give you this number, use this number as opposed to the rounded 24 when we're talking about isotopes. So in nature, this makes up 78.7% of the magnesium out in the universe. The magnesium 25 is about 10% and the magnesium 26 is about 11%. So most of the magnesium that we have out there is going to be magnesium 24. Now the number that you see on your periodic chart, that 24.3, that is all of these values averaged with their relative abundance. And sometimes people say, well, can you just add all three of them together and then divide it by 3? That would work if it was 33%, 33%, and 33%, but it's not. This is the biggest chunk, right? 78.7%. So we need to take that into account, that it has a bigger weight. Kind of like when you grade your weighted, when you try and calculate your weighted grade. So your tests are worth the biggest percentage, so they have the biggest bang for their buck. The homework isn't quite as much, and neither are the labs, right? So a C in here is going to pull you down a lot faster than a C in these other 2 areas. So let's look at carbon 12, carbon 13, and carbon 14. I want you to tell me the number of protons, the number of neutrons, and the number of electrons. This one and this one, the first and the last, should be easy. The neutrons you have to do a little bit of calculation for. So go ahead and try that. All right, so it shouldn't be too difficult. For carbon 12, the number of protons is always going to be 6, not 12. This is talking about the whole mass, not the protons, okay? Sometimes it can be written like this. Sometimes it could be written with the 6 in the place of the atomic number. I don't really like to write that in because that's sort of redundant, right? If it's carbon, that's obviously going to be 6. So where do you get that number? You have to pull it off the periodic chart. So 6, 6, and 6. Protons don't change. There's no charge in this corner here, so the electron should also be 6, 6, and 6. Neutrons are going to be this subtracted from this. So 6 here, 7 here, 8 here. We get heavier as our isotope gets heavier, but the only thing we change is neutrons because they have a mass, but they don't have a charge. Okay, so for this one, I want you to go in the other direction. So I want you to write the atomic symbol for the atoms with the following subatomic particles. So I want you to write something where you've got the symbol, you've got your mass in the upper corner, and you've got your atomic number in the lower corner. What happens if there's a charge? We'll talk about charge in a little bit later, okay? So we'll definitely go over charge and how that is affected with electrons. Just not there quite yet. So in these, there shouldn't be a charge for any of those. All right, so going this way, we have to do sort of a little bit of detective work using our periodic chart. So if we're looking at A, we need to figure out what element this is. So if I have 8 protons, just looking at the periodic chart, I know that it has to be oxygen. There's nothing else it can be. So I'm gonna put oxygen. You can put the 8 down here. There's no charge because this and this equal each other. So I don't need to put anything in the upper right-hand corner, and we'll talk about that anyway in a little bit. Neutrons, 8 neutrons. So in order to figure out the atomic mass, I need to take this number and I need to add it to this number. So this would be oxygen 16. Okay, next one here, 17 protons. All right, we're dealing with chlorine. So I can put the 17 down here. I need to add that 17, also see that these are the same, so no charge. 17 plus 20 will give me 37. So this is chlorine 37. This one here, 47 protons, so a little bit of a bigger guy. What are we, silver? Okay, Ag. And we've got to add that. So I'm gonna put the 47 down here, and we need to add that to our 60 to get our total mass, which is what, 107. Or AG 107. Any questions on that? You can throw it in the chat or pull your mute off and just ask. All right, moving on. There we go, got it. Oh, which of the pairs are isotopes of the same element? And which of the pairs do both atoms have 8 neutrons? Okay, so this isn't the same element because it's 8 and 7. This is the same element because it's 6 and 6. This is not the same element because it's 7 and 8. If we want to figure out the neutrons, we need to take 15 minus 8, 15 minus 7, 12 minus 6, 14 minus 6, so on, and find all the ones that have 8 neutrons. I don't really want to go through all that. So here's one of the pairs. They are the same because they both have 6 protons. And which of the pairs do both atoms have 8 neutrons? Okay, if we take 15 minus 7, we get 8. If we take 16 minus 8, we get 8 as well. So 8 left over for our neutrons. So the trickier thing, I mean, it's not super hard, but you got to do a little bit of math when we're calculating the atomic mass. So when looking at chlorine, for instance, chlorine has an atomic mass of 35.45. Why isn't it exactly 35 or exactly 36 or exactly 37? Well, because 75.76% of it is chlorine 35. The remaining 24 quarter percent of it is chlorine 37. So we have to average these guys together using the relative percentage to get this total number. How do we do that? So they will give you the percentage. So they'll give you an experimental percentage. And we just take the percent abundance and we multiply by the mass and we add each of the isotopes together. So I'm gonna write out, but we don't use the percentage as a percentage. We wanna use it as the fractional percentage. So if it's 88%, I want to change that to 0.88, okay? Or I want to divide it by 100 or move the decimal over 2 places because I want to get the percent gone. So we take the fractional percent of isotope 1 and multiply it by mass of iso 1. And then we add that to the fractional percent of isotope 2 times the mass of isotope 2. Okay, so here's all the information for the first one here, and we add it to all the information for the second one. These two things are getting multiplied by each other. I know that's kind of messy, but hopefully it'll be a little clearer on the next slide. So let's see what they did with chlorine 35, because chlorine 35, chlorine has just 2 isotopes. So you take your percentage, well, you have your mass, right, of each of them. If it gives you the more detailed version, use that. So if says, hey, chlorine 35, but it's really 34.97. Use the 34.97. If they don't give that to you, just use 35 in its place. So we need to get rid of the percentage. So we divide by 100. And then we take our mass times that, and we'll get some sort of value. Then we'll take the mass of the second guy times its fractional percentage, and we'll get that. And then we add those two together, and we end up getting 35.45. So this is a way to get a weighted average, as opposed to, oh, well, let's just add both of them together and divide by 2. You can only do that if it was a 50-50%. Now, what if you had more than 2 isotopes? Well, then this list of things that you need to add together would get longer, right? If you had 12 isotopes, you have to multiply 12 masses by their relative abundances and then add them together. You'll probably only get a problem that has 2 or 3. So here are some of the isotopes for lithium. Don't worry about having all the isotopes memorized. Okay, I don't expect you to know every single isotope for lithium, carbon, oxygen. Just know that there are isotopes out there. So lithium, we have a lithium 6 and we have a lithium 7. So when we average with their percentages, we get 6.941. So I can already see from this number that there's going to be a lot more lithium 7, right? Because the number is closer to 7 than it is to 6. So the more prevalent isotope is the one that it's closer to. If we've got carbon 12, carbon 12, carbon 13, carbon 14, but my average mass is almost on 12. Most of the carbon out there is carbon 12. Same thing here, 16 is really, really common. There's just trace amounts of 17 and 18. Well, let's do a calculation. All right. Gallium. So what is the atomic mass of gallium? And I don't want you to just do, just look at the periodic chart. I want you to actually calculate it out, okay? Because I may give you a theoretical element on an exam that you can't pull off of a periodic chart. So we have gallium, it's gallium 69, but its actual mass is 68.926, so use that. And its weighted percentage is 60.1%. So the first thing is divide that by 100 and divide this one by 100. We also have gallium 71, so just 2 isotopes. So I want you to set it up, try and work through it, and then we'll go over it and we'll do one more after that. And if you're having any trouble on like where these things are coming from, just ask me or throw it in the chat. I'll help you out. All right, so for this one, first thing is to take the mass, the more detailed value of the mass, and multiply it by the percent divided by 100. So you can either move the decimal over 2 spots or divide it by 100. And you end up getting 41.42 AMU from gallium. 69. And then 71 is really 70.925. So we're going to multiply that by its fractional abundance, and we get 28.30 AMU from the gallium 71. Add those together, and we end up getting 69.72. Now, note this number, your final number better fall somewhere between these two numbers. If you're averaging those together, they should fall in between there. What happens if your number ends up being really, really big and you don't know what happened? You didn't divide this by 100 here. That's usually what ends up going on, is people will take this times this, and then they end up with a really massively big mass. A really massively big mass, yes, a large mass. So if it's not fallen between your 2 isotopes or 3 isotopes, then you've probably gone awry right here. Okay. Yeah, I guess we'll talk about electrons. Why not? So a rainbow forms when light passes through water droplets, and it spreads out or refracts, so that you can actually see all the different colors and the different wavelengths that are contained in white light. So a rainbow is a form of electromagnetic radiation. There's all sorts of different forms of electromagnetic radiation. We detect it with our eyes, so light, colors of the rainbow, anything that we can see, that's all electromagnetic. That's all part of the electromagnetic spectrum, specifically in the visible light spectrum. And then there are energies that are higher than the visible light spectrum and energies that are lower than the visible light spectrum, or lower energy levels. So the things like lower energy would be radio waves or infrared. Higher energy things are going to have a shorter wavelength. They're going to be things like X-rays or gamma rays. So remember, low and long, okay? Low energy radiation has long waves. High energy radiation has short waves. So if you're sitting on a float in the water and you have really long waves, you're gonna go up and down and up and down. And there's gonna be this sort of slow quality to the rocking. So low energy, okay? If you're in a situation where the waves are coming much faster because the wavelengths are shorter, you're gonna be like up, down, up, down, up, down, up, down. That may make you a little sick, right? Higher energy happening there. So looking at an atomic spectrum, so when we have a specific element and we heat it up, so over there on the left, there's some barium, and we heat it up and it has this like greenish color to it. If I was to take that light and pass it through a prism, it would spread out and show a series of bands of color that would look like this. So we wouldn't get the complete color spectrum like we do in a rainbow or from white light or natural light. We would get incremental lines. And this light spectrum is specific to barium. So if you had a mystery element and it had a line at like this dark blue and this blue, and you knew how to read these two, like the green close, you could actually determine, hey, this is barium, because only barium will produce this sort of spectrum. If we're burning hydrogen or sodium, it's going to pop up lines of light at different places. So each element has its own unique atomic spectrum. The lines that we see in an atomic spectrum are associated with the changes in energy of the electrons. All right, so as the electrons move to a higher energy level, and then they relax back down, they release energy. And the way they release energy is in the form of light or color. Increase in energy as the value of n increases. So we've got these principal quantum numbers. So you can think of it like if I have my nucleus in the center, electrons that are closest are going to have lower energy. Electrons that are farther away are going to be higher energy. Why? Because the center of our atom is a positive charge. The electrons are a negative charge. So the nucleus is sort of sucking the electrons in. So in order for the electron to move from, say, here out to here, you got to pump energy into it to get it excited. So if we increase our n value, so we could say that this is n equals 1 and this is n equals 2. To increase our n value or our quantum number value, we would have to pump energy into it. How could we do that? We could charge it with electricity, plug it into the wall like a neon light. We could also put it in a flame. So one thing to note, the energy of an electron is quantized, and that's just a fancy way of saying that it can have only specific energy values. So it can be either at n1 or it can be at energy n2. We're not going to have it hanging like halvesy here. This is like the rung of a ladder. You're either on the first rung or you're on the second one. You're not hanging in between. So here is the full electromagnetic spectrum. You will want to be able to order these, identify them, all right? So visible light sits right here. It's actually a quite narrow range on the electromagnetic spectrum. I mean, it's really important for us, and we are such center-focused, narcissistic people that we think, oh, well, this is where the whole world lives, right? In the visible light spectrum. Well, our whole world lives in the visible light spectrum, but there is this whole world of energy outside of that. So if at lowest energy is going to be over here, remember low and long. So lowest energy, longest wavelengths. Highest energy is going to be over here. So when looking at this, red light actually has a longer wavelength and lower energy than purple. Purple has a shorter wavelength, higher energy. If you've like ever seen chakras or into like alternative medicine, they always say like if you need to ground, you can bathe yourself in red light. If you need to energize, right, purple light is more energizing, I guess. It's a really narrow window. I doubt you would feel it. But outside of this, the wavelengths you definitely feel, right? Gamma rays, you would feel that, okay? Radio waves are relatively harmless. So again, electrons and energy levels, they're quantized. I'm gonna see if it goes back to, it doesn't, okay. So real quick, while we're here, I wanna talk about the ordering. So we've got just on the outside of this right here, the red, we have infrared. One way to remember it, red touches red. So we can't see infrared, but there are ways for us to see it if we have equipment like infrared glasses or goggles or cameras. There are some animals that can see in infrared, right? So some reptiles can see body heat and things like that coming off. A little bit of a longer wavelength is a microwave. So satellites and cell phones use these microwaves, and then a microwave actually uses a microwave. And what's really cool about a microwave is that the wavelength at this point is at the exact right length to slip past a water molecule and hit it. So it will go into the food and the wavelength will come through, and every water molecule it finds, it'll hit the water molecule. And when it hits the water molecule, the water molecule will spin. And anytime something starts moving or spinning, we're creating thermal energy. So you heat your food up. So that's how your food gets heated in the microwave. The microwaves are actually hitting the water molecules in the food. So if you put food in the microwave that has no moisture or water, it's not gonna do anything. And we move outside of that, we got our television, then we got our radio waves. So that's thinking of your AM, FM, and your power lines. These are the things that we like send out into space. We go on the shorter spectrum. This stuff is all relatively harmless for people. Obviously, the visible light spectrum is harmless to biological. That's why we can see in it. I mean, it's not a coincidence. It's like a biological thing, that the thing we see is also like the most conducive for our material, our body. This stuff is all harmless. But as we increase in energy, this starts to become more detrimental to biological cells. So right outside of the purple light is ultraviolet. Ultraviolet UV, so coming from the sun. In little doses, this is good. You can get some vitamin D from it, gives you a nice tan. If you spend too much time in ultraviolet, you'll get sunburn, you can get skin cancer. So it will start to break down organic material. If you go higher energy than ultraviolet, you move into X-rays. X-rays have such high energy that they can move through your flesh and skin, and then it can create an image of bones. So, you know, an X-ray every now and then isn't going to hurt you, but the person who conducts an X-ray stands in a room outside of the room you're in, right? They stand in a concrete box somewhere. And then they usually give you some sort of lead thing to cover your special areas, because your ovaries and sperm are especially susceptible to X-rays. Just FYI. Gamma rays, those are the things that come from the sun, right? So if we didn't have our electromagnetic spectrum, or if we didn't have our magnetosphere, which is the thing that surrounds the globe, it's outside of the atmosphere. It's created from the moving magma in the core. That keeps us safe from gamma rays. So it shuts this down from getting to the Earth. If we lost that and we were getting hit with gamma rays, we would get sick very quickly. You can also find gamma rays. We do find it in small doses on the Earth's surface near radioactive stuff. So it's really, really icky. All right, so we talked about electrons with the same energy are grouped in the same energy level. So if all the electrons that you're looking at are have the same energy, and say it's N2, they'd all sit like books on that shelf. If this purple guy like all of a sudden got an increase in energy because we ran a current through it, he could go up to N3, N4, or N5. So what happens is energy is absorbed. So we send energy into the material through electricity, through heat, through a bunch of different ways. And the electron will move to a higher energy shell. And then when it relaxes back down, okay, so when this, because it can't stay excited forever, right? As soon as I unplug the neon light, these things can't be excited anymore. Or the electrical current or whatever it is going to go to the atom next to it and excite that one instead. So once this falls back down, it has to release that energy somehow. So the way that it releases it is through low energy light emission in this case, because this didn't go up very high in energy. It only went up like one rung. So the energy that it lost is pretty low. So we would expect to see sort of like a red light. Now, let's say in this case here, if we absorb a lot of energy, we give this thing a real big kick, it's going to jump to a really high orbital, really far from the nucleus. When it drops down, it's going to create a much more high energy light emission. So you're going to get green or blue or purple. So now when we go back and look at this thing, what we're actually seeing in this light spectrum is the energy from the electrons being released. There's some electrons that got excited to like the orange level, so a mid excitement. Then you've got a couple that got excited to a really high energy level, and they're releasing things like blue and purple. So for electron arrangements, the electron arrangement stuff for this class is going to be really simple. Okay, so for my people who were in 092 and you had the 1s2, 2s2, 2p6, 3s2, all that stuff, you're not going to need to know all of that. All right, it's going to be pretty basic. So we're going to have energy level, which is the first energy level. The first energy level can hold 2 electrons. So hydrogen is number 1 for its protons. So it's 1 for its electrons as well. So we have 1 electron in the first shell. What about helium? Helium is different than hydrogen in that it has 2 protons. So looking at our periodic chart, I can see it at number 2. So it has 2 electrons. So we're going to stick 2 electrons in that first shell. If we start going into some bigger guys, okay, the first shell is filled, but remember the first shell under this system can only hold 2 electrons, right? The second shell can hold a total of 8 electrons. So once we've filled those 2 electrons, we got to, because we're always going to fill lower energy first. We're always going to fill electrons closer to the nucleus because it's just easier, right? It's the path of least resistance. So if we're at lithium, we'll fill the electrons first, the 2 electrons in that first orbital. And then the remaining electron is going to go into the second. Okay, and as we just move across the periodic chart, we've got beryllium, boron, carbon, nitrogen, oxygen, fluorine, chlorine. Each of these is getting an increase in the number of protons. And so we're going to also say, because none of them are charged, that it's getting an increase in the number of electrons as well. So this guy will have, all of them have 2 in the first because that's been filled. So beryllium builds off of lithium's back, right? There's 2 there. It had the 1, and then we added 1 more. Then we added 1 more, 1 more, 1 more, so on and so on, until we get all the way down to neon. And neon is a noble gas. Neon has 8 in its outermost shell. That makes it particularly stable, okay? Anytime we have 2 in the first, so really this would just be for helium. So helium gets 2. But other than that, it's going to be 8. Anytime we get 8 electrons in that outermost shell, it's stable. All of these, not stable. None of those are stable. That's why they like to take on electrons or give up electrons. These guys are happy where they are, so they tend to not bond. Let's go to a little bit bigger. What happens if we go past neon? So we go into sodium. Well, then we need to start filling up the third shell. So the first shell holds 2. All the other shells are, for this, we're going to say hold 8. And I believe we're only really, well, I guess we go a little bit farther. Okay, so the third one will hold 8. So again, moving across from sodium all the way over to argon, 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8. These guys in the first and the second become sort of useless because they're complete sets. So I'm like never going to come in and grab an electron from here, very rarely. But these things on the outermost shell, these are called valence electrons. Valence electrons are what have to do with bonding. I'm sure it's written somewhere in the slides, but it just felt like convenient to say there. So the outer electrons are known as valence, V-A-L-A-N-C-E, valence electrons. So if I was to look at phosphorus here, phosphorus, it has 15 electrons, but it only has 5 valence electrons. So 5 of the electrons we could work or play around with in bonding. Okay, if we move into the 4th period, so on your periodic chart, hydrogen is in period 1, right, or row 1. Lithium is in period 2 or row 2. Sodium is in period 3 or row 3. Potassium is in row 4. That's where the transition metals start to happen. So in that case, our first is still 2, 8, 8, and we're filling the 4th in with 1. Now, if we go a little bit farther, this is how they are each going to be filled in. So we've got 2 in the first, 8 in the second, 18 in the third, 32 in the 4th, 32 in the 5th, 18 in the 6th, and 8 in the 7th. I'm not going to have you guys do a bunch of stuff in this, okay? Where the lantholides are, we're not going to spend a whole lot of time. So if you remember from 092, we had like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? You don't have to do the p's in this class. I'm not asking you to do p's and s's and any of that stuff. You don't need to tell me the shape. All you need to do is write it like this. You tell me how many are in the first, how many are in the second, okay? So oxygen is gonna be 2, 6. That's gonna be the electron arrangement. There's 2 electrons in the first because we filled them both up. And then if I look at where oxygen is, there's a total of 8 electrons. So the remaining electrons, the remaining 6 electrons are in the second one. Phosphorus is number 15, so it also has 15 electrons. So I fill my 2, I fill the second one 8, and I start plugging some things into the third. Calcium is 20 electrons, so we get 2, 8, 8, 2. So let's do a couple. I want you to write the electron arrangements. We're not doing electron configurations. I just want you to write the electron arrangement for each of these. I'll do the first one. So carbon has, ask yourself, how many protons does it have? It has 6 protons. So in this case, it also will have 6 electrons. So I'm going to have 2 electrons in the first one, and that can only hold 2. So the remaining electrons have to go into the second one. We will say 4 electrons in the second one. Why is 8 the stable number? It is the stable number. It is what the universe has given us. It's just a complete outer shell. Yeah. It does matter that it's stable. Why it's stable? Because that is just how our reality has been set up. Maybe there's a parallel universe out there somewhere where 7 is stable, but 8 is just particularly stable. The shapes of them get pretty funky looking. We're not going to talk about the shapes. But yeah, that's what it is. Two is stable just for helium. 2 is stable just for helium, yes. So the noble gases all have that stable outer electron configuration. And I don't really like the way that this is taught with the 2, 4. I like it better with the shapes and the 1s and the 2s. I just feel like it makes more sense, and you can get an idea of like how you can have electrons in a lower energy level that get filled after a higher energy level, but this is what it is for this class. So we have to do organics, so we're going to keep this simple. All right, so silicon is number 14. So I have 14 electrons. So 2 in the first, 8 in the second, that's 10. So then 4 remaining in that last one. Oxygen is 8. So we have 8 electrons, 2 and 6. Nitrogen is 7. So we fill 2 and then we fill 5. It's really not going to go past that with electron configurations. So just do it that way for this class. I guess is, okay. Where are we at time-wise? Oh, yeah, we can do a little bit more. Sure, why not? Trends in the periodic chart. So this is more concept-based here, but one thing we can talk about trend-wise is atomic size, ionization energy, and then metallic character. So when looking at your periodic chart, the atoms in the lower left-hand corner are the biggest atoms. Okay, so one way is to remember 87, Fat Frankie. So he's the biggest guy. This one doesn't have that row, but those are the biggest. The smallest are going to be in the upper right. Obviously, we're going to get bigger as we move down because we're increasing like the onion layers of our electron shells. So this one is just the first onion layer. This is the second onion layer, the third, the fourth. We're adding electrons. It gets a little trickier going this way. Why are we getting smaller as we go this way? Because aren't we adding stuff? Yes, we are adding electrons, but all the electrons are being added in the same onion layer. Okay, we're not like going to a bigger onion layer, we're filling in the same onion layer. And what are we also increasing as we move this way? The number of protons. And what do protons do? They have a positive charge, so they pull that electron or that onion shell closer to them. Okay, so that's why we get smaller as we move this way. As far as ionization energy is the amount of energy it takes to pull the electron away. So down here, this is the lowest ionization energy. Fat Frankie and rubidium, it's really easy to take an electron from them, like super easy, because they're so big and they're metals, so they don't even want the electrons anyway. They're like pretty much throwing them away. Now over here, minus helium, okay. Over here, like around fluorine, those guys have a really high ionization energy. They do not want to give up an electron. Like they're super greedy for electrons. Non-metals all want to take the electrons. As far as metallic character is concerned, most metal-like lower left-hand corner, least metal-like upper right-hand corner. Follows the zigzag line that we've talked about separating metals and non-metals. So Fat Frankie is the biggest. He's got the lowest ionization energy and he is very metallic. I feel like the slides are going to expand on that and everything I just said. There's going to be a slide for each one of them. I haven't looked at these slides since, honestly, I haven't looked at them since before I had my baby. So, but I do know all the information. I know it all. Just haven't had a refresher on this for a little bit. Okay, so group numbers and valence electrons. So I had mentioned that idea of a valence electron. So a valence electron is the number of electrons in the outermost shell. Inner shells don't matter because we assume that they're filled and complete. So valence electrons correlate to your group number. So let's look at the main group elements. So we've got column 1, which was hydrogen, lithium, sodium, potassium, rubidium, cesium. That's column 1, it has 1 valence electron. All right, column 2, beryllium, magnesium, calcium, so on, that has 2 valence electrons. All right, going over to boron, 3 valence electrons. Carbon's row, or carbon's column will have 4 valence electrons. Nitrogen will have 5 valence electrons, so on, all the way over to the noble gases, which would have 8 valence electrons minus helium. Helium has 2 valence electrons, but it's still satisfied with the 2 valence electrons. So if I was to say, hey, how many valence electrons does chlorine have? You'd say 7, because it's in the 7th column. It's the easiest way to calculate it. Calcium, 2 valence electrons. Fat Frankie, 1 valence electron. Okay. I am going to stop there. I don't want to get into dot structures. Okay, that's it. So if you have any questions, let me know. Stay around. If you don't have any questions, log off so I know that you don't have questions for me. Have a good weekend. I will check on the lab thing. If you're still having issues, just email me the lab, but I'll try and get that figured out. Okay? Bye. Good to see y'all.